Okay, so we're continuing talking about chapter 8, right? And last class we were talking about polar molecules. We reviewed how to determine if a molecule is polar. We reviewed intermolecular forces and how to determine what intermolecular forces are present and which ones are going to be the strongest. And we talked a little bit about the intermolecular forces being related to the phase, I believe. Is that correct? So stronger intermolecular forces are going to make for condensed phases, right? Yes. And weaker intermolecular forces will give you non-condensed phases, such as a gas, right? Everybody's with me, remembers?
Yes.
Cool. Awesome. So now we want to continue the conversation about gases. Okay? So gases are especially different from condensed phases because they are very dispersed and they have very low densities. Right? And I think we talked about this maybe a little bit in the first chapter or two, but we're going to get into it in detail, right? So the properties that a liquid or a solid have are incredibly different than properties that a gas has, right? So just thinking about your guys' world experience living in the world, what is the gas that you're most familiar with?
Oxygen.
Oxygen, but specifically, there's a mixture
O2.
that we breathe. So the air, right? No, that's okay. So
Yeah.
so this is a really common
Carbon. I don't know.
You guys are feeling spunky this morning. I like it. Yeah, that's respiratory. Yes. But what I'm trying to get to is the mixture of gases that you're most familiar with is air, right? Air is comprised of about 19-ish% oxygen, O2, has about 79% nitrogen, and about 1 plus or minus on a humid day % water, and then other trace gases. Right, so this is the composition of air, right? So this is the one we're most familiar with. How do you experience air? What does it feel like? So let's contrast this with some condensed phases, right? So if you are experiencing a liquid, what does that feel like? It can be a stupid answer. It's okay.
Well, you can experience liquid in different ways. Like
right?
You can take a shower or you can hydrate.
So sure, yeah. Yeah, but I would say that the number one describer of liquids would be wet, right?
She's got
it.
it.
Yeah, totally. Does that make sense?
Yeah.
What about solids?
They're dense.
Yeah, they are. Yes, totally. How do we experience them? What are you experiencing underneath your butt right now?
My bed.
Right. So they could be squishy, they could be hard, they could be elastic, right? So solids have a lot of properties that we can experience. Liquids have a few qualities that we can experience. They tend to be pretty similar, right? But what are the experiences that we have with a gas? How do we interact with a gas?
It allows you to breathe.
That's true. Yeah, but is that a feeling? Is that a sensation?
I mean,
Well, can you
you
smell
more
it?
so feel it with like the lack of breath.
Yeah, so you can feel the air molecules filling up your lungs, right? You could feel the, I think somebody else said another one. Was it Steph? Did you say something?
Yeah, I think it was wrong. I said smell it.
No, that's completely right. Absolutely, you can smell a gas. Not all gases, but yeah, absolutely. Wind, that's a great one, Kata. So when you experience wind, right, you can feel molecules bouncing off of you, right? That's literally what the wind is. Does that make sense? Or at least as we experience it, right? So the other thing that we can experience in terms of a gas is temperature, right? So on a day, like a couple days ago where it was really, really hot out, right? We're experiencing gas molecules moving really rapidly, right? So heat in terms of gas particles means that the gas particles are moving faster, right? Faster molecules mean more collisions. That's what makes us feel hot, as it were, right? Those collisions with our skin are increasing the temperature of our skin by transferring energy from the molecules in the air to our body, right? So that's like the most complicated way of thinking about how we experience temperature, right? But I think it's really helpful in terms of starting to see a picture for what gases are and how we experience them, right? So does that kind of help you guys think about more how we're experiencing these things? Cool. So in terms of gas properties, there's a couple of really important properties that determine what a gas will act like, essentially. Those properties are pressure, which is represented with a daddy P. And are you guys familiar with any units of pressure?
Guilty.
Say again? PSI is one. Yeah, absolutely. So that would be pounds per square inch. That's a stupid American one, but yep. We got millimeters of mercury. Thank you, Madison. Absolutely. Do you guys ever look... I ask this question in every class, and every class looks at me like I'm an idiot. Do you guys have a weather app on your phone? Do you ever check the pressure, the barometric pressure? So the barometric pressure is usually hovering right around 30 inches of mercury. That's, again, another stupid American unit, but millimeters of mercury would be the metric equivalent, but inches of mercury is also a common one, right? When the barometric pressure gets higher, that's usually an indication that there's going to be storms, I think. I'm not a meteorologist, right? Low pressure means hot weather. I don't know. I'm making this up. Don't listen to me. That's not a science I'm versed in. But yeah, so these are a couple different examples. Millimeters of mercury are often referred to as torr. Also, they're just two names for the same unit. This one is not the same unit. It's an American unit, right? But we can convert between these three, okay? The other one that we're going to work with most commonly is going to be atmospheres. Whoa. Which are represented by ATMs. atmosphere. I think I spelled that right. I'm going to write it down here so you guys can actually see it. Better? So, these are all different units of pressure, but they're all representing the same quantity. And pressure is defined as a force exerted over some area, right? So, for example, if I push my hand down on this piece of paper, right, I'm exerting a force, and the area that I'm exerting it is the area of my hand, right? So that would be a force applied per some area. Does that make sense, guys? Cool? Cool. All right, so the next quality of a gas, or the next property of a gas that's going to be important, is the volume of gas container, right? So we're not necessarily talking about the volume occupied by the gas particles, right? Because that's not a very big volume, right? Because we know that the actual particles are very spread out and they're very small, right? So when we're talking about volume, we're talking about the volume of the container of the gas, right? And I think you guys are relatively familiar with volumetric units. The ones that we're going to use most commonly here will be liters, Daddy L, or milliliters, right? Questions? We good. Cool. The next one that we're going to use to characterize gas, is the number, I'm sorry, this is represented by the letter V, Daddy V, the volume of the container. Number of moles, which is represented by little n for number. And this is essentially looking at the amount of gas particles. Everybody cool with me? Cool. And then the last one that we have to characterize the gas is temperature. Which is represented by Daddy T. Now we've talked about, I believe, 2 different units of temperature, besides Fahrenheit, because we don't care about those in science, right? We've talked about degrees Celsius, yeah? And we've talked about, and Kelvin, exactly, right? So temperatures can be represented in degrees Celsius, I think that's right. Or Kelvin. Kelvin. Daddy K. Okay? And we'll talk more about these units and how to go between them. Okay? So these are the 4 qualities that characterize a gas. So now we're going to talk about the equation that allows us to relate those characteristics, okay? And that equation is called the ideal gas law, okay? We'll talk about why it's ideal in just a bit. So the ideal gas law has the pressure times the volume is equal to the number of moles times a constant R times the temperature, okay? So R is the gas constant, and it's the constant that relates the four properties of the gas, right? So pressure, volume, number of moles, and temperature are all related by this factor R, okay? Specifically, the R value that we're going to use most commonly will be this one, and it has units of liters times atmospheres per mole Kelvin. Okay, so that number we will use a lot. You guys still all right with me? Cool. So there are other gas constants that you can look up that have different units, but I think it's a huge pain to look up a gas constant every time you're trying to do one of these problems. And I'm going to ask you specifically to use this one in certain cases. So you're going to need to know how to convert from other units into these. Okay? So what do I mean by that? Let's say you have a problem asking you a problem that gives you a volume in milliliters, a pressure in millimeters of mercury, and a temperature that's in degrees Celsius, right? So do you guys see how none of these units match the equivalent units in the gas constant?
Yeah.
Right? So what should our volume unit be?
Liters.
Should be liters, right? So in this case, we would need to convert to liters, right? What about our pressure unit?
Atmospheres.
Atmospheres, exactly. So we'd need to convert this to atmospheres, right? What about temperature?
Kelvin.
Kelvin, exactly. Does that make sense, guys? So one of the most important things for you guys to be able to identify at this point, and one of the reasons why I harp on you so much about it at the beginning, is being able to identify what units are pressure units, right? What units are volume units? What units are temperature units, right? Because knowing that is what allows you to know what you need to convert to get your dimensional analysis to work out. Does that make sense? You guys tracking live? Cool. So let's do a practice problem. Okay, so what is the volume of a balloon at 26.5 degrees Celsius with 0.0250 moles of air and a pressure of 745 millimeters of mercury? Okay, so first thing we need to identify, what are we trying to solve for in this problem?
Volume.
The volume, absolutely, right? So just thinking about our gas constant up here, what unit are we going to find our volume in?
Liters.
Liters. Is everybody okay with that? Steph?
Yes, I'm good.
Cool, cool, cool.
Like, why this question? Like, why?
Why?
Well, this question may not seem as important, but let's say instead of talking about a balloon, we were talking about your lungs, right?
No,
So-
I mean, that didn't make condescending at all. It was just like, wait, what?
So yeah, no, that's okay. But yes, that's completely common in these types of problems. There's going to be a lot of really seemingly arbitrary questions that you're like, why the do I care about this? I don't, right? And that's okay, right? But just believe that there are analogous questions that definitely have medical applications and absolutely have importance. Right?
Yeah, there is a purpose, sorry.
No, but that's okay. Honestly, seriously, you guys, if I don't understand the point of doing something, it makes it really hard for me to motivate myself. You know what I mean? Like, so that's, if you need help getting motivated with these, I'm with you. I got you. Okay, so we're looking for a volume, right? And we expect the volume is going to be in liters, right? Again, I'm guessing liters because my gas constant has units of liters, right? And so when I solve for the volume, I'm going to need all of these other units to cancel out. Does that make sense? Cool. All right, so now let's look at the variables that we're given here, right? So we're given the temperature, which is 26.5 degrees Celsius, right?
Can I ask a stupid question?
Not at all. Go ahead. Yeah.
So if we're looking for volume, do we want to adjust the law to like divide out P and like do it to the other side and then okay.
We're gonna get
okay.
Yep. We're gonna get there. So the first thing that I want to look at is making sure that you guys understand whatever units you're given in here, right? First have to be translated into these units.
Okay.
Right? So in order to get temperature into the right units, we need to get it into Kelvin, right? Is everybody with me?
Yeah.
Cool. So how do we convert from Celsius to Kelvin? Anybody remember?
There's a conversion factor.
There's a conversion factor. And it's actually relatively simple, right? So all we have to do is add 273.2, and then we have Kelvin.
That's easy.
That's it.
That's it. And I'm never going to ask you to convert from Fahrenheit to anybody else because it's stupid, and why? So, but you will have to know how to convert from Celsius to Kelvin. That's very important. You can never, ever put Celsius in here, okay? Because the temperature of a gas has to be the absolute temperature, right? Not the relative temperature, which Celsius is the temperature relative to the scale on which water boils and freezes, right? You see what I mean by being a relative scale versus an absolute? Kind of, sort of? Cool. Cool. So we've got 9. Yeah? Did I math? Cool. So, I've got my temperature in the correct units. Now, I've got my N, number of moles. Do I need to do anything to convert that guy? No, we're good there.
Moles is in the thing.
Yep.
So,
Exactly, right? So moles is in here, moles is here, we're good. All right, and then lastly we have our pressure, which is given as 740, oops, excuse me, 700, oh my God, 745 millimeters of mercury. Holy moly, that was hard. And what unit of pressure do we want?
we want atmospheres.
That's right, we want atmospheres. So the conversion factor to get you from here to atmospheres, for every 1 ATM, there's 760 millimeters of mercury, right? So, what's going to go on the bottom here? Steph, you're muted.
Oh,
No, go ahead. I was just gonna say what you were gonna say. 1 millimeter of mercury.
Hmm?
Right?
What's our conversion factor say?
Oh, my bad. 760.
Yeah. That's okay. It's good. And 1 atmosphere goes up top, right? So now we've canceled out our millimeters of mercury.
Mm-hmm.
And so what do you guys get when you do that math?
.9802.
We'll just call it 0.98.
Okay.
Okay. You guys like my nerd wallet updates that you get to see while we're doing this? You guys get to know so much about my personal life.
frequent Amazon shopper.
I'm trying to do less of the Amazon. I just feel like there's such a horrible company, but it's like so easy.
It's so easy. I get it.
Yeah, it's hard. Okay, so now I have all of my variables in the correct units. That's what I'm saying, right? That's what I'm saying. Oh man, it's so sad. I feel bad. But like also, if I wanted to buy 25 pounds of squirrel food, like it would cost so much more at any other place, you know? I'm gonna go to PetSmart and it's gonna be so expensive. Mommy ain't got that kind of money. Okay, cool. So, next thing we want to do is get our perv-nert equation down, right? And we want to rearrange it to solve for the variable that we're looking for, right? So the variable that we're looking for in this case is the volume, right? So how do we get V by itself?
Divide out P.
That's right. Divide both sides by P. This P cancels out, and we end up with V is equal to N times R times T divided by P, right? So now all you have to do is plug in these guys, right? Oh, and this guy. You need that guy too, right? So what do you guys get for the volume? I'll give you a minute.
Wait, I'm confused how to plug the numbers in a little.
Yeah.
So you have the N is the moles,
Mhm.
correct?
Oops.
Like you just start plugging in. Okay.
Oh my God, I can't write.
And then with the R,
Mhm.
the 0.08206.
Yep. This guy.
Sorry, y'all.
It's okay.
This
I
is
just
big.
don't. I don't have enough room here to plug all of that in.
Okay.
I got 6.274.
Okay, hold on.
Liters. Let's see.
I got the same.
Cool.
Yep. Got the same thing.
Awesome.
Good job.
You guys are killing it.
Okay, but units. So
Okay. So, I might have a slight disagreement with you guys here.
Uh-oh.
So, 0.0 or 0.627? 0.627, not 6.27.
Oh.
That's not what I got.
Are you in scientific notation?
I don't think so.
Okay.
Would you get? Can you repeat the answer one more time? Yeah, I got 0.627.
I got the same thing.
Mm-hmm. Okay, so let's just make sure that we're all putting everything in right. So I'm sorry, I'm going to go from here up here because that's the only place on this page I have room. So we would have V is equal to 0.025 moles.
Oh, that's where I messed up.
That's 0, right?
It's
Yeah.
0.025. I put
Yeah.
I put 0.25.
Yeah, that's what I figured.
Got it. Okay, that'll change my answer.
Oof.
Wow. Divided.
This is very ugly, and I'm sorry, you guys.
Love it.
Atmospheres. Right? So, just to make sure our units are good, right? Pretend like this is being multiplied up here. If we're multiplying 1 over k times k, right? These guys will cancel out, right? Again, we're pretending that the temperature is right here next to it. Yeah? Steph, you with me? Cool. You're muted.
Yeah, I'm good. Thank you.
Yeah. What? Oh, you can't read the this thing down here? Yeah, because I made it ugly. I'm sorry. I'm just trying to show you that the units cancel. Yeah, no, they're really ugly. Liters times atmospheres divided by moles times Kelvin is what's written here.
So we're going to be left in liters.
Exactly, right? So we have moles cancel with 1 over moles. And then up top here, ATMs will cancel with the ATMs on the bottom. We'll do another problem, which will be cuter than this, so that we can actually see the units. Yes. Is that a little better? So, moles up top cancel with moles on bottom here. Kelvin cancels with 1 over Kelvin here. And the ATMs on the bottom cancel with the ATMs on top. The unit, sorry, one sec. Alex, the units for the gas constant are given. Right? So that's R, the gas constant. And that's here. Right? Yeah. Yes, exactly. Sorry, go ahead, Steph. What was your question?
So now with my calculate, like I put it in again,
Yeah.
and I'm getting a different number. I got 0.616. So
0.616. That's probably, I'm guessing you might have gotten these digits mixed up.
maybe okay.
But you're close enough. And how do you cancel the moles? So you got moles up here, and then you've got 1 over moles here. Does that make sense, Alex? So if you want to write it a little bit more clearly,
Well, it's technically on the bottom. It's kind of hard to explain.
sorry, this is liters. I just made it really hard to see, right? No, so what we have here are nested fractions, right? So if we were just looking at the top first, right, we have moles being multiplied over here and Kelvin being multiplied over here, right? So these guys will cancel here, these guys will cancel here, and that leaves us with liters times atmospheres, right? Which is divided by ATMs, right? Yeah. Does that make sense, guys? These are all really, really good questions, because if you can't see this now, it's gonna trip you up later on. So if it helps you to go piece by piece, canceling things, go for it, right? But I would say the number one mistake that students make when they're doing PervNERT questions is they accidentally will do something like, let's say I'm trying to solve for n here, right? If I want to solve for n, what do I need to do to get it by itself?
Divide out RT.
Divide out RT, right? So n should be equal to PV divided by RT, right? But I don't know about you guys, it's really easy to accidentally, when you rewrite this, right? Right? Which is not correct.
Correct.
And the only way that you would know that you made this mistake is because your units wouldn't cancel properly. Does that make sense? Cool. Any other questions? We're okay? Yes, well, absolutely. We're going to do another one, yeah. What was that one thing that I was going to say? Any other questions about the previous problem that we did, though? Everyone all right with that one? Okay, cool. So, let's say we want to know... Sorry. Sorry. Keep moving it around. Okay, so the pressure of 1 mole of gas is 765 millimeters of mercury at 30 degrees Celsius. What is the volume occupied by the gas? So, what are we solving for?
Volume.
Volume, right? So we expect our answer to be in liters, right? And we have our number of moles is 1. Our pressure is 765 millimeters of mercury. Is that the unit of pressure that we want? No, what do we want?
ATM.
ATMs. So how do we get from millimeters of mercury to ATMs? What needs to go on the bottom?
760.
760 millimeters of mercury for every
1 ATM.
1 ATM. Exactly. So what do we get for the pressure in atmospheres?
I got one. Oh.
Yeah?
Yeah.
Everyone all right with that? And our temperature is 30 degrees Celsius, right? And what unit do we need it to be in?
Kelvin.
So how do we convert from Celsius to Kelvin?
At 273.2.
Oops. Did I math?
Yes.
Cool. And we need our PV equals nRT, right? We're solving for V. What do we need to do to get V by itself?
Find out P.
Divide both sides by P. So we end up with V is equal to nRT divided by P. So we'll have 1 mole times 0.08206 liters atmospheres per mole Kelvin times Kelvin divided by It's easy to mess that up, Alex.
I got 24.708.
Anybody else want to back her up? That sounds reasonable to me.
Cool.
Anybody else?
I got a 24.63.
I got 24.62, but
Cool. Yay.
Is it just a rounding thing?
Yeah.
Okay.
Oh, you mean like where to round?
No, because I mean, I don't know why my calculator would give me 24.7 if it's 24.6. I put in all the digits exactly how they are. Full. I didn't round anything.
So you didn't
Oh,
round
it's
this
that
guy?
Bottom.
Yeah.
It's the bottom.
Yeah. So if there are numbers that you didn't round, then that's going to change the answer slightly, right? But if you got a 0.7 and I got a 0.6, that's basically the same thing, okay?
Okay.
Does that make sense?
Yeah. I'm just not trying to get it wrong.
No, totally. And this is another important point, guys. So one of the things that I really, really, really want to point out before you take the exam, that I think everybody's experienced on the quizzes to date, is that especially with fill in the blank type questions, I can only put in the permutations of the answer that I can guess that you guys might put in, right? And those permutations don't include spelling errors, right? Sometimes they include gaps where you didn't put a gap. So any of those little things, even capital letters, can make it say that you got an answer that's wrong, even though it's actually right, okay? And I will always go through and correct those for you guys, okay? So please, please do not freak out if that happens to you. If you're confident in your results, that's great. I will let you know after the fact if what you got was wrong for some other reason, or if it was just a spelling error, I'll give you those points back, right? Or something like that. Does that make sense, guys? Yeah, no problem. I think, and this is true for the labs also, right? So, especially for those of you who aren't in my lab, I'm just barely getting started grading some of the most recent labs, but make sure that your instructors are going through and double checking your answers and giving you credit even if something is slightly different than the way that it was put into the answer key, right? You guys can see the answer key after the fact, right?
I had a question about labs.
Yes.
For the this week's nomenclature labs and next week's lab, let's do the balance and reaction lab. Once you submit both of them, there really isn't an answer for each problem. So I'm just a bit confused. Are we gonna get like an answer key after the date the due date goes over? Yeah,
so I'll send out a message to the 100L instructors and make sure that they understand that they need to go through and grade. But also I can make it so that I think there's still a few sections this week that haven't had nomenclature due yet, if that makes sense. So
right, so you're just gonna wait until the due date has passed. That
exactly.
When you give out the answer to
exactly.
Okay.
Yeah. So for the nomenclature and also for the balanced chemical reactions, I'll make sure that the answers go out as soon as all of the sections have turned them in, right?
And do you go through lab as well as quizzes and exams?
Absolutely, yeah. And so should your lab instructors, right? So if you put in the right answer, but maybe it was spelled wrong, that shouldn't be a reason to get it incorrect, right? They should be giving you the points back for that. So.
Okay, thank you.
Yeah, absolutely. And again, I will let them know. I think there's some instructors that are relatively savvy with Canvas, and then a lot of other ones who aren't. So I'm literally having to go in and post these modules for other instructors because they don't know how to do that. So I'm not surprised if they don't know how to make the answers visible either. So I'll do that for them, for you. So I'm pretty much managing 11 sections of lab right now. Yeah, it's fun.
You're getting paid overtime, right?
No. Nobody ever pays teachers extra for them doing extra.
Yeah.
Hence the reason why teachers are this job is a bummer. I love my job, don't get me wrong, but nobody pays me to do extra stuff for you guys. Most students, I think, are pretty receptive about that fact. They get it, but some students are very much not. Yeah. So yeah. Questions about how we got this answer? How are we feeling with this? So we pretty much did.
This would have been stoichiometry.
We haven't gotten there yet, but we're gonna do that with this. I'm purposefully putting off that part of this chapter because I don't want to overwhelm you guys. But starting Monday, we will start doing gas stoichiometry problems, right? So we've pretty much talked about most of chapter 8 in terms of the gas material. What I want to do on Monday is talk a little bit more about the types of problems that we can see, right? So Monday will be a lot of problem solving. Okay? Questions? Turn this off.